Hello, everyone, and thanks for joining me on this discussion on independence. So, independence in probability modeling means that knowing that one event occurs or does not occur does not change the probability of the other event. If two events have that relationship with each other, they're independent of each other. For example, results of two consecutive tosses of a coin. Whatever you get on the first toss does not impact what you're going to get in the second toss. And the main implication of independence is that probability of A given B, it's now probability of A. So if A and B are independent, then the knowledge that B occurred does not change the probability of A. So you can basically simplify it to probability of A. And you know that's a huge simplification in our calculations if we know two events are independent. Because dealing with a conditional probability is much harder than dealing with a simple probability like this here. I give you a real life example. Let's say tomorrow is rainy is one event, right? We don't know the probability of that. And buying Netflix stocks is another event. And there are two completely independent events because knowledge of one is not going to change the probability of the other. For example, probably that you buy Netflix stocks given that tomorrow is rainy is no different than probability of just buying Netflix stocks because the additional information that tomorrow is rainy does not change your decision. So now remember that the main implication of independence in our calculation is that probability of A given B is not probability of A. So conditional probabilities will be gone if they are independent. So you recall the multiplication rule that we had. Probability of A intersection B was probability of A given B times probability of B. Now if I tell you that A and B are independent, how does that change? Well, it changes to probability of A times probability of B now, right? Because probability of A given B is now probability of A, since they're independent. And this is the key condition to check whether two events are independent. You check the probability of their intersection, and if that's equal to probability of one times probability of the other, that means they're independent. So that's the key condition to check. Well, if two events are independent, these three statements will be true. But they all boil down to the last one, which we had up here. Because probability of A given B, you remember, is probability of A intersection B times probability of B. So that is the same as this. So that's why I'm telling you that the key condition to check independency is this. And keep that in mind whenever you're asked if two events are independent given some information. This is what you need to be using to check them oftentimes. But a very common confusion is between independence and mutually exclusive, because they kind of sound like the same thing, but can A and B be mutually exclusive if A and B are independent? And the answer is no. And let's read this paragraph very carefully, and then I'll give you some examples after that. The answer is no, because if A and B are independent, that means knowledge that A occurred does not change the probabilities that B may have occurred. That's the definition of independence. Whereas, if A and B are mutually exclusive, knowledge that A occurred does change the probabilities that B may have occurred. In fact, it means B never occurred because they are mutually exclusive. Let me give you an example. Let's say that I and two of you are playing a dart game. It's me and Antonio and let's say Lisa, right? And probability of hitting the bullseye for each one of us is different. Let's say for me is 20%, for Antonio is 30%, for Lisa is 40%. Okay? And you agree with me that these three events are independent. Probability of me hitting the bullseye is independent of whether Lisa is hitting it or not. These are independent events, but are they mutually exclusive? They're not, because all three of us can hit the bullseye. And that's kind of in the Venn diagram, that's kind of the intersection of those three events. Me hitting the bullseye, Lisa hits it, and Antonio. The intersection of those three is when we all three hit the bullseye. Let me give you another example. If two events are mutually exclusive, for example, on the roulette wheel, black and red are two mutually exclusive events. Probability of them are the same, but they're mutually exclusive. You cannot have a result that is both red and black. But are they independent? The knowledge that the roulette wheel is going to land on a red outcome totally changes the probability of black. In fact, it means if that's the case, probability of black is 0. So the knowledge of one changes the probability of the other. So mutually exclusive events cannot be independent. Let's take a look at one example on the roulette wheel. Are red and first 12 independent? Right? This is something that you probably can't say off the top of your head. You need to work on it and show it mathematically. Essentially, that question means, does the knowledge that red occurred change the probability that first 12 may have occurred? Try to work it mathematically. So I told you that the key condition to check is here, right? But here instead of A and B, we have red and first 12. So we're going to check that. So the condition that we want to check is probability of R intersection T1 is equal to probability of red times probability of T1. Well, we know that probability of red is 18 over 38, right? If I go back to a roulette wheel slide, you see here that we have 18 reds, and the total outcomes in the sample space is 38 outcomes, so 18 over 38. Probability of T1 is 12 over 38. And the R intersection T1, how many outcomes do we have in R intersection T1? So this is T1, right? And the reds that are in the T1 are 1, 7, 5, 3, 9, and 12. So there are 6 outcomes in that intersection area. So probability of red intersection T1 is 6 over 38, right? So let's go back. Probability of T1 is 12 over 38, and probability of R intersection T1 is 6 over 38. Now, you obviously can say that 6 over 38 is not equal to 18 over 38 times 12 over 38. And because they're not equal, and this condition is not met, you would say it's not independent. So that's how you check whether two events are independent or not. In our probability modeling, a lot of time for if it makes sense that a few events are independent, if it just makes sense, we assume that they're independent. We do not prove it. The last bit of independence is if you have a set of events, collection of events from A1 to AK, and they're independent events, then probability of their intersections is just multiplication of their probabilities. That's what this means. So what it means is the key condition that we had here can be expanded to more than two events. If A1 through AK are independent events, then probability of A1 intersection A2 intersection all the way to AK is equal to probability of A1 times probability of A2 times all the way to probability of AK. That's what this means. Let's look at one example on independence. Historical data suggests that 42% of the orders received by a computer company originate from universities. 75% orders received include a request for monitor, and 15% of the orders request overnight shipping. A computer order is received. What is the probability that the order originates from a university and includes monitor and overnight shipping? Assume independency of events. Here is an example that you really can't prove it right now that these events are independent, but you can safely assume that because it just makes sense that they're independent, but we're not sure. We assume it. So if that's the case, what is the probability that the order that you receive has all those three characteristics? And here there are some keywords. It says the order originates from a university and includes a monitor and overnight shipping. So clearly there's an intersection of these three that we're interested on. So let's say that, this 42%, we call it probability of university. We call this probability of monitor, and we call this probability of overnight shipping, O. And here we want to calculate probability of U intersection with M intersection with O. And because they're independent, what we learned here is to calculate their probabilities, you just multiply their individual probabilities. So probability of U times probability of M times probability of O, which is 0.42. And that is equal to 0.047, about 5% chance that an order has all those three characteristics. Let's wrap up this section by these two simple prompt questions here. If A and B are two independent events, then what is the probability of B given A? Well, if they're independent, the condition here is irrelevant. Probability of B given A is just probability of B. Write an alternative expression for probability of A intersection B using additional probability to what was presented today in class. And if you want to use conditional probability to define this, that is the multiplication rule. Probability of A intersection B is probability of A given B times probability of B.